Let's take a look at Hooke's law. So this thing here. Now Hooke's law, we have a restoring force is equal to K, which is a spring constant. It's just a constant. And S is the extension of the spring or stretched, stressed, compressed or bent object. So the definition then in written words is this. We have when an object is bent, stretched, stressed or compressed, all right, that's kind of the intro to it, the restoring force is proportional to the extension. That's the main part of it. And then there's a little bit at the end, provided the elastic limit is not exceeded. And what that's telling us is that F is proportional to minus S. So the force is proportional to the extension, but the restoring force is a little bit different, and we'll see that in a moment. The restoring force occurs in the opposite direction to the extension, which is why we've got a minus there. Now the questions you should be able to answer at the end of this video are what is the restoring force, what is the extension, and well, I've done that already. What do you think the formula is to link these together? F is equal to minus Ks. Right, so let's go to this FET applet. And what we have is a spring that's at rest. It's got a length here that is its normal length, or what I often call its natural length. And we have a claw or I don't know, some sort of clamping device that can stretch this thing with an applied force. So let's apply a force to it, and we see that when we apply a force to it, the string is pulled to the right. So we're exerting a force on it, and that's causing the spring to extend. And the extension is beyond its original or its natural length. So that's where it is. Here, let's say that's a line representing its natural length. And if I exert a force on it, we can see then that the extension, which is from its original position to there, that's the extension. And we can see that the greater the force that we exert on it, the greater the extension, so the longer the spring becomes. But the extension is always from the natural length position out to where it is when the force is exerted on it. So again, one last time. That's the natural length, and then the extension is the distance that the string is stretched to the right of that. In other words, we're looking at the distance from there to there, and we're ignoring the rest of the spring. So that's what the extension represents. Let's have a look at the restoring force. Now you can see that there's a force pulling this to the right. There's an extension to the right as well. And if you look on the right-hand side here, I've said that the force is proportional to the displacement, but they occur in the opposite direction. So the force that we're exerting on the spring here with this clamping device is not the restoring force. The restoring force is what the spring is trying to do. And the spring, or the stretched string, the spring in this case, is trying to pull the spring back into its original shape. So if I let go of this, there would be a force acting on the spring that would allow the spring to go back. It would vibrate or oscillate for a little bit of time, and then it would come to rest at the natural length. So if you look, the displacement is from there to there in one direction, and the restoring force is the force that the spring is trying to exert on itself to go back to its original position. And they are indeed in the opposite direction. You'll also see that as I increase the pulling force there, the restoring force increases, and if the restoring force increases, the displacement increases as well. So let's go back to these three questions then and make sure that we can answer them. What is the restoring force? It's the force that the spring exerts on itself in order to get it to go back to its natural length. The extension is how far the spring has been extended beyond its natural length, and the formula relating the two, well, if we start with F is proportional to minus S, then to go from a proportionality, which basically is a straight line graph through the origin, something like that, to an equals, what we need to do is put in a constant of proportionality, which will somehow be related to the slope. So we get F is equal to minus Ks, where K is related to the slope. It's either the slope or it's 1 over the slope. Now there's only one last thing that we need to deal with here, and that's what this thing is, the elastic limit. And what it comes down to is if you stretch a spring, eventually the spring can be bent out of shape. And when it's bent out of shape, it will no longer go back to its natural length. So that's when we exert too large a force on it. And what happens is, if we exert too large a force on it, it distorts the spring, And as a result, the force will no longer be proportional to the extension. We get a graph that curves or bends a little bit. And then when you leave go of that spring, like I said, it doesn't go back to its natural length because the spring is damaged.